And we're going to continue right on to the last talk of this session, which is NASA testbed environments for Artemis lunar surface operations, given by one of our leaders at this workshop, Kelsey Young.
Thanks, Marie. So first of all, I'd like to thank my co-authors. I represent a very large and very integrated team pulling from the EVA office, from the Flight Operations Directorate, from the EVA Tools Group, and from our communication colleagues at KSC. So next chart, please. We've heard a lot about field-based testing simulations, but I'm going to kind of narrow the scope today to talk about some of the on-site at Johnson Space Center testing that we've been doing to really bring together a really integrated operations team. I think every speaker this week has emphasized the importance of bringing together this integrated team to accomplish exploration objectives. And we've been doing that, as Alex Kanellakos briefed yesterday, within the NASA environment. So the pillars of this interaction so far are operations, exploring what the procedures, protocols, and operational concepts exist for doing Artemis lunar surface exploration, what tools and hardware we need to develop to support that science operations, and also what training we need to do. We're working on developing training plans for not just astronaut crew members, but also mission support personnel. And that includes cross-training both for flight controllers and engineers to understand science, but also scientists to understand how to exist in this operations and FOD environment. So this interdisciplinary NASA team already exists, and we're hard at work in a variety of these testing environments, which I'll brief today. And the future Artemis science team, which we're here this week to define, will be able to readily integrate into this already existing testing platform when they're brought online. Next chart, please. These next two charts are charts that Alex briefed back in the May LSSW in the tools and instrument sessions, and they're important things to consider for us as scientists when we want to influence operations into a design for lunar surface exploration. So when you're working on a tool or piece of hardware, a procedure, protocol, software to support operations, these are things to consider for us as the scientists. We want to, prevent injury and risk, of course. We want to create designs and operational concepts that are reliable, that are efficient, that reduce workload. We want designs that are upgradable, especially considering the longer term phase of lunar surface exploration, as well as feed forward to Mars. We want to be able to maintain these designs on EVA, fix them on EVA. We want them to be flexible and work in a variety of different operational concepts and testing environments. We want them to be testable. I'm going to talk a lot about that in the next few minutes. We want them to be compatible with a variety of different operational concepts, as well as compatible with other existing hardware. And of course, we need to be able to train them and fit them into this training infrastructure, part of which you heard Jackie and Alex talk about yesterday. Next chart, please. So the first objective, of course, of any human spaceflight mission is not science. It's to bring the crew safely home. So we as scientists need to take part in that methodology and make sure that we need to minimize risk to all of the activities that our astronauts do on an EVA. And we also need to think about, removing risk, complexity, and human error by taking those factors out of a design. So these are things that all of us need to consider when we're thinking about tools, hardware, software, and even operational concepts and procedures. We want to make sure that these designs can be evaluated early by an operations team and through these integrated tests we've heard so much about this week, and that they also can be incorporated into whatever crew training takes place, as well as mission support training. Next chart, please. So now we're going to get into the actual exploration EVA testing. And so there is a lot of testing that's currently ongoing. I'm going to brief you on a few different types of tests we've been performing to develop hardware, ops, and training to support Artemis. This early testing has included representatives from the EVA office, from flight operations, from the astronaut office, from stakeholders from science and EVA tools and the spacesuit, as well as representatives from crew health and performance and even the informatics system. And the chart you see here was briefed by Alex yesterday, and this is kind of the sort of architecture for flight ops that we're envisioning for the Artemis program. And what we're here to talk about this week is sort of the bottom right part of that chart with the EVA science officer and any of the flight control team support teams and what that architecture looks like and what the infrastructure is that we need to support it. And that's what the breakouts are here to talk about today. Next chart, please. So the first type of testing that we've been completing in the last couple of years is flight controller part task trainers. These FCPTT tests were used often in shuttle and are used frequently for International Space Station today to train members of the flight control team. And our integrated FCVA ops team has performed 2 such FCPTT EVA mini sims in 2020. We've included, some of our objectives have included early integration of notional and representative science objectives at notional science landing sites. We've exercised these flight control team comms protocols with the EVA science officer position. We've done some initial assessments of cognitive workload as well as delayed comms representing what we're going to experience on the moon. And we've worked on developing timeline and procedures. Our future sims will include more integrated science objectives, navigation and crew tracking objectives, assessments of EVA data information flow, and we're really trying to create a space for when that broader Artemis science team is brought online, there's a way to integrate into already existing sim environments. Next chart, please. We've also been completing a series of tests at the JSC Rockyard. This is a planetary analog facility that's on site at the Johnson Space Center. There's a picture there. It's been used in the past for hardware development, and it was even used back in Desert Rats, like you heard David and Cindy talk about today. And our integrated operations team has conducted a series of sim events at the Rockyard during 2020 safely in the COVID environment to develop tools, test operational concepts, and that's included 3 one-crew tests to get some early feedback on some of our Artemis EVA tools, as well as 5 tests with 2 crew members to start to evaluate workload in the JSC Rockyard. Some of our objectives have included end-to-end sampling procedures, including curation protocols. We've been able to provide some early and frequent feedback to the EVA tool team for some of the geology tools. We've worked on developing procedures and cuff checklists, as well as refining real-time comms and imagery requirements to support science operations from a mission control perspective. And we've worked on refining the roles and responsibilities across the exploration EVA system, evaluating roles like the EV crew member, the role of the IV or CAPCOM, the role of the EVA science officer. And we look forward to bringing in even more roles and responsibilities like we'll talk about in breakout number 2 today. And we're also working on just developing the Rockyard as a training facility for future Artemis crew members. Some of our major takeaways are that the Rockyard is really great to efficiently and quickly advance tool design and operational concepts work in between these larger, more integrated field-based test events that we've heard so much about today and yesterday. More work is needed, kind of narrowing in scope to flesh out the trade space of task workload for 2 crew members during science operations. And a lot more work, we've heard about this today as well, is needed in developing procedures and task tracking products to support science operations. And our future test, the next of which will be next Tuesday actually, will begin integrating notional science payloads with operations as well as evaluating operations in lower lighting conditions. Next chart, please. Beyond the Rockyard, we're testing in the Neutral Buoyancy Lab and in the Active Response Gravity Offload System, or ARGOS, which enables us to simulate operations in microgravity and in lunar and Martian gravity. Actually, right now, as we speak, there's testing going on in the Neutral Buoyancy Lab to simulate Artemis lunar surface operations in a lunar yard that was developed in one corner of the Neutral Buoyancy Lab. These facilities are great for, again, tool development as well as for suited operations. In that picture of the MBL there, you can see a prototype planetary surface exploration suit as well as operations with a Kirby Morgan dive helmet, which enables us to flexibly test a lot of these operations concepts and tools. And we conducted testing during 2020 to evaluate tools, operational concepts, and performance metrics. Next chart, please. Just a little bit about facility scale. On the left is that Rockyard picture. In blue is the outline of the Neutral Buoyancy Lab, and in sort of the darker blue is the lunar yard corner of the Neutral Buoyancy Lab, and in red is a map of the current ARGOS facility, which is the smaller rectangle, and planned larger gravity offload system in the sort of bigger red rectangle, superimposed on the Apollo 11 traverse map to show kind of what the scale of these things look like. And then on the right, we see zoomed out from JSC. JSC is kind of at the center of that bullseye imposed on the Apollo 15, 16, and 17 EVA maps, just to show that, we're really dealing with a much smaller scale than what is really needed for what we hope to get to accomplish science objectives on the lunar surface. And if you go to the next chart, I'm going to say what you've heard almost every speaker, I think, talk about this week, and that's, of course, we have to be able to test in the field with a really integrated group of scientists, engineers, and operators to be able to bring in that high science fidelity and the more realistic science objectives, not to mention the higher fidelity scale of operations. This is great for training for engineers, flight controllers, and managers. You heard Lauren Edgar talk about this yesterday. We've been working with our academic and other government partners. And it's really a great complement to the JSC facility testing that we currently have going on. And we're really excited to integrate with much larger swaths of the science community once we get the Artemis science team stood up. The next chart is my final chart. And that's, I didn't talk about VR today, but we've also been complementing our JSC facility testing by virtual reality testing as well, and as well as, of course, building toward future testing in more integrated ways and in field environments. Science is already thoroughly integrated with the Artemis flight control team in the 3 key phases Alex briefed yesterday. In the planning phase, we have early integration of science priorities into mission planning and hardware development teams, and testing is already underway in multiple facilities. In the area of training, we're hard at work developing training plans, not just for astronauts, but also for cross-training mission support personnel from flight controllers all the way to scientists. In terms of the fly phase, we're already building science representatives into the flight control team, and we're accommodating future science team members to be brought on board. And we're refining the role of the EVA science officer through this integration and ongoing testing. And the bottom line is we can't wait to incorporate the broader Artemis science team. We look forward to the breakouts to discussing what this team is going to look like. Thanks.
Thank you very much.